Okay, so this is Bernoulli problem number 6. And these 6 through, I think it's 9, 6 through 9, no, 6 through 8, sorry. Yeah, 6 through 9 were developed when I was teaching fluids. So they were developed to help people combat the issue that I notice a lot of people have. Oops. It's me. I notice a lot of people have issues with being able to differentiate this P with this key Z. So a lot of people, they want to use, you learn hydrostatics, rho key H, and they want to just plug that into this P, and they tend to have issues. They double count for, what's above it. Okay, so the question asks for, I think, the volume, the flow rate. Okay, so flow rate is velocity times A. Okay, so all the V's you see on this board are velocity to start off with. And we start off with our famous Bernoulli equation. Just to give you guys, so at this point in the fluids class, if I was going to teach this, you would notice they would barely touch upon it, so they really wouldn't know a whole lot more than you guys about this. But basically, when you have a tube like this, it denotes the velocity there would be 0. Stagnation point is what we would call it in fluids. And here, the velocity is not 0, so the velocity just loops past. Okay? It just goes on by. So I'm going to evaluate this point 1 to this point 2. And the reason I know to do that is I've put little manometers to look at the pressure. Okay? So those tell me the pressure that's going on. Okay. So they tell me the hydrostatic pressure at this point and the hydrostatic pressure at this point. Now notice I put the datum here, but they're really along the same line. So I let both the Z terms go to 0. They cancel. You'll notice a lot, one of the other common assumptions to make in Bernoulli is not only that the area is so much bigger than the other area, so the velocity goes to 0, but you'll also hear a lot of times, the elevation difference is insignificant. And I'll try to find an example of that. I really haven't seen one in the textbook. I'll try to look for one and just maybe present at the beginning of next discussion, next Tuesday. But that does tend to be one of the common famous assumptions. Oh, okay, well the elevation head's barely changing. But that's not really what's going on here. Really what's happening is that they're at the same elevation. Now the velocity at 1, I've told you this is what we call a stagnation point. At this point in the fluids course, you would have learned that if you have this, you would have that. You guys aren't expected to know that, so I'm telling you that. Okay. And so from the Bernoulli equation, what you get is this. You get V2 squared over 2 times rho P1 minus P2. Now, you don't have enough information to know P1 and P2 individually. What I tell you, actually, is by me writing this delta H, I'm telling you the pressure difference, okay? So P1 minus P2 is the pressure difference between this point and this point. And so what I can write now is this delta P, okay, is equal to P1 minus P2. And that's actually going to be delta H times rho G. And that should remind you of hydrostatics, okay? So delta H times rho G. And so when you combine these two equations, then that's when you're going to see, okay, well, if I plug this delta H rho G for this P1 minus P2, I have that here, divided by 2 over rho, so these rows obviously cancel because what you see here, and this is squared, so you take the square root of that and get V2. And then after that, it's just simple that Q is equal to V2 times A2, okay? And on one of your worksheets, I think it's number 13, I have Q and M dot both defined. M dot is the mass flow rate, Q is the volumetric flow rate. So Q is velocity times area, and dot is density times velocity times area. So in this one, I asked for the volumetric flow rate. And the area too. So, I write 0.01, it's just to let you guys know that you know the area basically. So the areas are all knowns in these problems. And so, but I'm asking for this point. So if we were to find it here, it would be V1. But because we've put one of these kinds of meters in there, then you don't know V1. So you know V2, and you multiply that by A2, and that gives you the volumetric flow rate. Okay. Let's see. How do I shut this off?